Hello and welcome to the third and the final module in the fourth week of getting started with competitive programming. As you know, this week we have been talking about applications of the disjoint set union data structure, and as our final example I want to talk about a problem called War. You can find this on the UVA online judge. The problem ID is 10158, but you don't really need to remember that because as usual a link to the problem statement is in the description of this video, and this problem is also available on a platform called uDebug where you can find additional test cases and hints and things like that. So link to that is provided in the description as well, so do check it out. Now this problem has several things going on apart from an interesting story. There are a few different concepts to keep track of, so you might find that the description is a bit longer than usual, and in fact I think in terms of just the number of lines in the code for the solution to this problem, this is probably the longest that we have seen. Actually, conceptually it's a really clean problem once you get the hang of it, but I will say that it is a bit non-trivial and it takes some time to fully absorb all the moving parts and all the cases that are involved. So please be patient with this. It might take you some time before you can write everything out, especially if you like to write the solution out yourself before you follow along. So give yourself some time to make sure that you get all of the scenarios pinned down correctly. So with that said, let's begin as always by taking a look at the problem statement. So we are given that there are n people who are present at a party or something like this, so that context is not so important. But what we are given about these n people is that each one of them belong to one of two countries. So people who are from the same country, so here I've coded the two countries with a maroon and a black background. So for people who are from the same country, they are all friends with each other. So here we have a group of 5 mutual friends on the one hand and then 3 mutual friends on the other hand, and using the terminology from the problem statement, people who are from different countries, so if you pick any pair of people who come from different countries, we think of them as being enemies. Now that's a pretty strong word, so I might just call them rivals instead. So we have these friends and we have rivals. So that is the information that we are given to begin with. But the interesting thing about the setting is that you don't actually know who is from which country. So you have walked into this party and you see these n people, and you don't really know who are friends and who are enemies and so on. So the story goes that by observing people's behavior at this party, by looking at how they're talking to each other, how they're interacting and so on, who is getting into a fist fight, who is exchanging pleasantries, you can figure out, or you can make a pretty good guess about which pairs of people are friends and which pairs are enemies. Of course, you don't get to know all of this up front. You have to spend some time at the party to infer more and more information. So the way this is given to us is that as you spend time and you start inferring this information, you sort of make a record of it in your notebook or whatever. So let's say that you observe 2 people who are hanging out and having a good time, then you decide to make a note of the fact that they are friends. So this is given to you in the form of a query. Well, I guess you should not call this so much a query because it's not asking you for an answer, but this is something you can think of more as an operation. So you just make a note of the fact that these 2 people are friends. So this is something that will actually come through in your input. So your input is going to be a sequence of, you can think of them as a mix of these commands and queries. So we'll come back to the queries a bit later, but the operations are essentially going to be either make friends or make enemies, which is the query that which is the operation that comes in when you observe that there are 2 people who are very likely to be enemies. So both make friends and make enemies come with the IDs of 2 people on whom you want to impose either this friendship structure or this rivalry relationship. So as you continue to spend time in this party, you start building up your observations, and let's say you note them down. So whenever you see two people and you're convinced that they're friends, you make a note of that. If you're convinced they're enemies, you make a note of that as well. So formally, of course, the way this works out is that you're given a series of these make friends and make enemies operations as input, and you could just put them on the record as you go along. So let's say these are some of the relationships that you have been able to figure out by direct observation. Now, if you remember, what we said earlier is that there is this friendship and rivalry structure or network that we know exists among these people, and essentially what is happening is that as you spend more and more time as a neutral third-party observer, it's like you're building out parts of this picture. You don't know this picture, but it's like a few pieces of a jigsaw puzzle have been given to you, and you're trying to piece them together and hopefully eventually build up the complete picture as you go along. So far though, all the information that you have built up is from your direct observations. So an interesting aspect of this problem is that you can also build up a little bit of information from indirect inferences. So maybe you have not observed a pair of people directly, but you can draw some conclusions about them based on the other information that you have. So the way that you can do this is driven by the fact that these friendship and rivalry relationships, because of the way they are, they're driven by certain rules, and there are basically 3 rules that we need to keep in mind and see how we can use them to draw these additional inferences. So let's go through these rules. The first one is that friendship is transitive. What I mean by this is that if A is a friend of B and B is a friend of C, then A is also a friend of C. Notice that this behavior is not really very intuitive, in the sense that if you're thinking about friendships as in Facebook friendships, for instance, you don't really see transitivity, right? So for instance, if you have a friend, just because this person is your friend, you don't automatically become friends with everybody that this person is friends with. However, that is the case in the context of the story that we have in this problem. So let's just keep this in mind and take a look at our example and see if we can infer any new friendships here by an application of this rule. So remember, the rule simply says that the friends of my friends are also my friends, which is to say, if we apply it on a specific people, let's say A is friends with B and B is friends with C, then that implies that A is friends with C as well. So can you apply this to some 3 people in this picture and infer a new relationship? This would be a good time to pause and try and confirm this for yourself. Alright, so hopefully you've also discovered at least this one new relationship that you can establish between 2 people because they are in this chain situation that I just described. So this is one way of applying the first rule of friendship. I don't think there are any more inferences that we can draw just based on this rule. So let's move on to the second rule, which says that if you have a common enemy, then that makes 2 people friends. So if you know that A is an enemy of B and A is also an enemy of C, in that situation B and C have a good reason to be friends with each other because of this common enemy. Again, let's go back to the example that we have been looking at and take a pause here and see if you can develop or infer any new relationships based on this second rule. So once again, the second rule says that a common enemy makes 2 people friends. So can you find 2 people who have a common enemy? Alright, so you can probably discover that you can infer a new friendship between these 2 people here because they have a common enemy in the person who is the rightmost person on your screen right now. And I don't think there are any more inferences that you can make based on this rule because there are just 2 rivalry relationships that you have so far. So let's move on and talk about the third rule, connecting friends and rivals. So the third rule, which I think is also a popular saying, is that an enemy of a friend is an enemy. So notice that this is distinct from the previous situation. In the previous rule, what we said is that a common enemy makes two people friends. So these are two people who, at least as far as we were concerned, they were strangers. But let's say they have a chat and they realize that they both have the same rival, then that becomes a reason for them to become friends. Here, however, you have two people who are already friends, and one of them, let's say, realizes that the other person has an enemy. Then this person is going to declare rivalry with the rival of his friend, because that's just how this rule works. So if you are my friend and you have a rival, that person becomes my rival as well. Let's see how this rule plays out in our example. So take a look here and see if you can draw any new conclusions based on this third rule. Once again, remember the third rule says that an enemy of a friend is an enemy. So let's take a look, and if you need to, please pause here and try to figure out if you can apply this rule. Okay, so we do have a situation where someone has a friend who has an enemy, and you can see this playing out on sort of the bottom right corner of this picture, and that is definitely one extra rivalry that you can deduce from the picture that you had built up so far. And now just take a look at this picture once again and see if you can infer anything new based on what you have so far. Especially after this last relationship was added, was there anything new that can be concluded by applying one of the rules that we have discussed so far? Okay, so you might spot that here are two people who now have a common enemy, right? And because they have a common enemy, the second rule comes into play, and they become friends. So that's the picture that we have so far, and let's just move things around so that this is a bit clearer to see. It's the exact same picture, which the pieces adjusted a little bit, and I think hopefully it's at least visually clear that at this point you have a dead end in terms of indirect inferences based on the rules that we have discussed so far. So let's actually turn this around so that it's easier for me to draw the next connection that I want to draw. So suppose you have a make friends operation, and this is a new direct observation. So let's say that you make friends between these two people here. Then you can probably guess that by applying the first rule of friendship, which says that your friends are my friends, you can actually infer these two new friendships in this picture. But that's not all. You can actually say more based on one of the other rules. Can you think of any other relationships that you can derive from the three rules that we have seen before? Take a pause here and think about it. Well, remember that we said that if you are my friend and you have a rival, then that person is also my rival. So this was the third rule, and based on that, notice that if you pick any one of the people who are in a yellow circle and any person who is in a blue circle, then they are going to be mutual rivals for this reason. By the way, I should have mentioned this explicitly, but friendship and rivalry is always assumed to be mutual. It's never a one-sided relationship. That is also something that we are given. Okay, so let's not add these rivalries explicitly to this picture because it's going to make it crowded. But notice that there is one person who is kind of isolated from the rest of the picture that we have built so far. So let's say that we make a direct inference, a direct observation about a rivalry between the person on the bottom left of your screen and this person who sits in the component on the right. So what does this direct observation tell us? Can we infer something more from here? Well, if you remember, we said that if two people have a common enemy, then they themselves become friends. So you can probably identify here that these two people do have a common enemy. So you can infer this new friendship here. And from this new friendship, you can infer many more friendships. And I leave it as an exercise for you to build out the rest of this picture, fill in the remaining blanks, and see if there's anything that still remains to be inferred, if you need more direct observations to build up the whole picture, or are you really done from here? So do think about that when you have a chance. But in the meantime, let's move on to actually describe the task that we are supposed to perform. With all this background in place, I think we are ready to understand what we are supposed to do. So the input is going to be a stream of queries, and these are, well, some of these are actual queries, while the others are really operations or information about these direct observations. So we have seen two of these already. So you have make friends and make enemies, but apart from these, you will also get queries of the form our friends and our enemies. So for these latter two queries, you are expected to output yes or no based on the information that you have so far. So for example, if you're asked if P and Q are friends, then you're supposed to say yes if you have evidence that they are friends, either from a direct observation or by inference, and you can say no otherwise. As you might expect, it is similar for the are enemies query. So if you're asked if P and Q are enemies, you are supposed to say yes if you can deduce that they are enemies, either by a direct observation or by some sort of inference. And if this is not the case, then you say no. So your task really boils down to keeping track of this picture, the one that we were building up like in the example before, as you get these make friends and make enemies operations. And of course, the important thing is that you don't just make a note of the direct observations, you somehow want to also track all of the inferences, all of the implications that come out of applications of rules 1, 2, and 3. Remember, the first rule was that all friends of my friend are my friends as well. Friendship is transitive. The second rule was that if two people have a common rival, then they become friends. And the third rule was that if my friend has a rival, then that person is my rival as well. So you want to apply these rules as much as you can to actually infer additional relationships, to be able to come up with accurate answers to the our friends and our enemies queries, which is really the crux of what is going on here. All right, so let's also point out a little bit of fine print, which I think is important. So you might actually get make friends or make enemies queries which contradict your previous knowledge. So this could be as simple as the first line of input saying make friends 1, 2, and the second line of input saying make enemies 1, 2. This, of course, is a very direct example of contradictory behavior, but you could also have operations which contradict the knowledge that you have gained so far by inference. So even if these indirect conclusions are contradicted, you're supposed to ignore these commands. So you're supposed to ignore these operations. So here is how this works. Whenever a make friends or a make enemies operation does not contradict your previous knowledge, but it just adds to the picture that you're building, then you might do all this background work of making note of this information and drawing inferences and all of that, but you don't have to do anything in terms of output. So you produce nothing as output for the valid make friends and make enemies queries. But on the other hand, if you receive a query that contradicts your previous knowledge, then you output -1 to make a note of the fact that you encountered a contradiction, but you move on as if nothing has happened. So you simply ignore this query in the context of the picture that you are building. Okay, so that's how the problem works in terms of the input and the expected output. Now we really have to think about coming up with a solution. So of course you could try to brute force emulate everything. So you could add this information and you could go over all pairs, all triples, whatever it takes to exhaustively examine the impact of the 3 rules of friendships and rivalries that we discussed, but you can quickly see that that's going to be too expensive. So we do need to do something smarter. And where do disjoint sets come into this picture? Well, it's reasonably intuitive to think that the friendship relationship can be modeled using disjoint sets. Because of the fact that they're transitive, it would make sense to say that the friendships evolve in these clusters, and whenever 2 people from 2 different clusters are identified as friends, it makes sense to just mash the 2 clusters together, because transitivity will imply that now everyone in the first cluster will become friends with everyone in the second cluster. So I think it's pretty natural to use disjoint sets to keep track of the friendships, but the real question is, how do you keep track of the enemies? So that's some extra information that you do need to carry along, and you need to find some way for making room for this extra baggage in your disjoint sets data structure. Now, there are multiple approaches to this problem, and we will be describing a specific one, but I think it's really worth taking a break here and see if you can puzzle this out for yourself. I think it's a really cute puzzle to work with, so just give it a shot and join me back in the next part of this module. In the next video, we will talk about a complete solution to the problem, which involves using disjoint sets for the friendships and a little bit of extra bookkeeping and some case analysis to carefully track the enemies. So I'll see you there.